Thank you for coming, everyone. So today we're lucky to have Professor LynnCominsky presenting on gravitational waves. Dr. Kominsky received a BA in physics and chemistry from Brandeis and wanted to receive a PhD in physics at MIT and complete a postdoc at UC Berkeley. Professor Kominsky joined the faculty of Sonoma State University in 1986, where she has been chair since 2004. Professor Kominsky has led the education and public outreach program for NASA missions, including Fermi, Swift, and XMM Newton, and she is a co-I as well on the Fermi, Swift, and New Star missions. Professor Kominsky has won a wide range of awards, including being named a Fellow of the American Physical Society, Fellow of the American Association for the Advancement of Science, and the Sally Ride Excellence in Education Award and the Education Prize from the AAS. Most recently, Dr. Kominsky was awarded the 2017 Frank J. Molina Astronautics Medal from the International Astronomical Federation, and in 2019, she was selected as one of the first 200 Legacy Fellows named by the American Astronomical Society. So we're extremely lucky to have Dr. Kominsky talking to us today, and really looking forward to your talk. Take it away.
So one of the projects I've worked on, besides NASA satellite missions, including Fermi, about which you'll hear a little bit more later, is LIGO. So I've been working on LIGO for about 12 years now, and having studied neutron star and black hole binaries my whole career using X-ray and gamma ray satellites, it was really exciting for me to be able to get involved with looking at the same types of objects, but with a totally different kind of way of detecting them, namely gravitational waves. So in today's talk, I am going to tell you about the initial discoveries from LIGO that won the 2017 Nobel Prize for some of LIGO's founders. And then I'm going to give you updates on everything that LIGO and Virgo have seen since that time. But it all started off with this press conference that I was lucky enough to be able to attend back in 2016. This was held at the National Press Club in Washington, D.C.
Ladies and gentlemen,
and what you see on this stage is Dave Wrightsey, the head of the LIGO lab.
We have detected
Franz
gravitational
Cordova,
waves. We did it.
Gabriela Gonzalez, who was the LIGO spokesperson at the time. Ray Weiss and Kip Thorne, who were two of the people that would go on to win the Nobel Prize a little more than a year later. So let's hear the very beginning of this press conference. Okay, so what are gravitational waves? We're all really excited about it, but it would be good to know a little bit more about them. We usually explain gravitational waves by saying that they are ripples in the fabric of space-time. And they were predicted by Einstein in the general theory of relativity in 1915. And so what happens is if you look at the image on the left, you'll see a bunch of point masses around a central object. And as the gravitational wave passes through space-time, they compress and then stretch, and then half a cycle later, the compression goes in the other direction and the squeezing goes in the other direction. So it just alternates between stretching and compressing. Now, if you picture this circle of masses and then you go over into 3 dimensions on the right-hand side, you can see that it looks like a wave passing through as the wave travels through space-time. So that is what we mean by a gravitational wave. Now, you may be familiar with having seen pictures that look like this. This is our sun, this is the Earth, and this is a representation of space-time in this green and black grid underneath. And you see the heavier sun makes a much bigger curvature in space-time than does the lighter Earth. But these kind of embedding diagrams, which are useful for visualization, really are sort of incorrect, because in reality, the space-time is curved in all dimensions around the sun, right? So it's not just below the sun on a sheet. There's actually curved space-time in every dimension around any object. But of course, we can't draw things in 4 dimensions, and so we tend to portray things like this instead. But this is how Einstein saw gravity, as a curvature of space-time due to mass. Newton, as you may know, saw gravity as a force between 2 objects, that would be transmitted instantaneously according to Newton's gravitation law. The force that you experience depends on the masses and the distance between them, inversely squared. And then, of course, there's the apocryphal story of Newton sitting under an apple tree and seeing an apple fall and looking at the moon in the sky and realizing that it was the same force that was making both of those things happen. If we compare the views of Newton and Einstein about gravity, in Newton's world, space was flat and time is constant. In Einstein's world, space and time are intertwined, and you cannot easily separate them, right? That's why we call it space-time. In Newton's world, gravity is a force between two masses, but in Einstein's world, you have gravity just due to the curvature of space-time from a single mass. In Newton's world, the force of gravity acts instantaneously, and in Einstein's world, gravitational waves travel at the speed of light, which we use the letter C to represent. And in Newton's world, light travels in a straight line, whereas for Einstein, light follows the shortest path through curved space-time, so it wouldn't necessarily be a straight line. Now, what about black holes? Well, black holes are infamous for not letting light escape once you get within a certain distance from them, known as the event horizon. And the event horizon is defined as that region around the black hole where you need to be going the speed of light in order to escape. If a collapsed stellar core doesn't have enough mass to collapse all the way back down to a black hole, it'll make a neutron star, an object that has a surface and is very dense and small. Now, way back when I first started in X-ray astronomy, we were actually studying Cygnus X1. The very first black hole was discovered with X-ray rocket observations, and later the mass was measured by watching how the black hole affected the supergiant companion that it orbits around. And you can see that the two stars are tugging on each other, and so you can measure the radial velocity curve, and from that you can figure out what the mass of Cygnus X1 is, the unseen object around the big star. And it turns out to be about 16 solar masses, plus or minus 5. And this is typical of most stellar black holes that are made when a star reaches the end of its life on the main sequence, explodes in a big supernova, and when the core collapses down, if there's more than 3 solar masses of material, we think that it will collapse all the way down and make a black hole. And as far as neutron stars go, we have had indirect evidence for gravitational waves ever since the 1970s, when Joe Taylor and Russell Hulse discovered this pulsar named PSR 1913 plus 16. It's 2 neutron stars going around each other. You can measure the mass of both of them. They're each around 1.4 solar masses. And one of them is a pulsar with a 59 millisecond period. And so you can track the decay of the orbit as these 2 neutron stars orbit around each other. Einstein's theory of general relativity predicts a decay curve for the size of the orbit as the neutron stars get closer and closer together. And this orbit has now been tracked over more than 30 years, more than 40 years. And these red dots are the data points lying exactly on the curve as predicted by Einstein. And the error bars are so small that you can't even see them on this scale of this plot. So the orbital decay rate that we're seeing in this binary neutron star system is exactly what is expected when you lose energy from the system due to gravitational waves being emitted as the orbit shrinks. But that's indirect evidence for gravitational waves. We don't get to see the waves themselves in this system. Okay, so now this is actually a supercomputer simulation that I'm going to show that shows what happens when 2 black holes are orbiting around each other and then they merge. And all of the swirly stuff that you're seeing around the outside is lensed light from actually behind the black holes. And you'll see they develop these little whisker-like things. That's actually the other black hole's image being bent around. And now they've merged, and now it sort of rings a little bit, and then it relaxes and settles down. So this is not an artist's impression. This is actually a computer calculation using supercomputers done by the Simulating Extreme Space-Time project, using the full equations of general relativity. So if we could see the light from the black holes as they're merging, this is what it would look like. This is now a computer calculation of what the gravitational wave emission would look like from two merging black holes. And you can see the ripples propagating out on the space-time grid. And as the black holes get closer, the intensity gets higher. Then once they merge, you get this big blast. It just sort of moves out and goes through space. So that is what the gravitational wave emission looks like. And now a little bit about LIGO. So LIGO stands for Laser Interferometer Gravitational Wave Observatory. So this is a cartoon version of the laser. It goes through a beam splitter like a Michelson-Morley interferometer. Half the light goes down each arm of the interferometer, recombines at the beam splitter. Now we'll slow it down again. There you see the wave splitting off, going down the 4-kilometer arm of the interferometer, reflecting back at the mirror, recombining with the wave from the other arm. And when they combine for total destructive interference if the interferometer is tuned properly. So you see no signal on the detector. But as the length of one of the arms of the interferometer changes by squeezing and compressing of space-time from a gravitational wave passing by, you can get constructive interference and then destructive interference, and you end up with a signal at the output of the interferometer. So that is the greatly simplified version of how LIGO works. And now I'm going to show you a more realistic version of LIGO. We actually did this video. This is Hanford, LIGO at Hanford in Washington State. And this video uses the actual CAD drawings of the LIGO interferometer. That's what it really looks like, except these things are 4 kilometers long. And we're going to start off at the end where the laser is. Zoom in to see the actual path of the laser. So the laser starts out, it goes through a bunch of mirrors and reflects off of a bunch of things. HAM stands for horizontal amplitude modulator. It's something that seismically isolates each part of the LIGO optics. As you can see, it's a very complicated beam path. The MC stands for mode cleaner. Those are optics that clean up the frequency of the signal. The PR stands for power recycling, where we reflect the light back and forth a lot of times to build up the power in a certain part of the beam. There's the beam splitter. We'll back off again and show you the path of the light down the 4-kilometer beam length. When it gets to the end, it bounces back and forth at least 400 times, building up the power in each leg of the interferometer tube. It's actually a Fabry-Perot interferometer. And then if we travel down the beam line like the photons do, we get to the test mass mirror at the end of the beam line that does the reflecting. This is a 40-kilogram mirror suspended by 1 millimeter thick fiber optics. You see these little fibers here. And then the beams come back and they recombine at the beam splitter. And then they're going to be going off into the output optics, the output mode cleaner. So we're cleaning the signal back up again. And then eventually the beam gets to the output mode cleaner and then is read out from the optics of the detector. So now we'll see what happens when a greatly exaggerated gravitational wave passes through LIGO. We're seeing the length of the arms change, compress and squeeze. And then as the beam interacts with itself and constructively interferes, we get to read out a strong signal, which then goes away the next half cycle. And that is actually the waveform that we saw for the very first detection. Now, LIGO has 2 different observatories. The one that we showed you a little cartoon of before is at Hanford, Washington. It's up in the Nuclear Reservation near Richland. The second one is in Livingston, Louisiana, much different kind of location with a lot of forests and greenery around it. But you need to have two different observatories in order to make sure that the signal that you're seeing is actually not due to noise. Moreover, these two observatories are located about 10 milliseconds apart in terms of light travel time, and the legs of the interferometer are oriented opposite from the two sites. So that provides another check on the signals that get detected. So here's what LIGO observed for the very first time, the very first merger of two black holes emitting gravitational waves discovered in September of 2015. And the figure on the left shows the data from LIGO Livingston. The figure on the right shows the data from LIGO Hanford. In the case of one of them, it was flipped upside down, so they look the same, because otherwise, due to the different orientations of the two sets of legs, they would look opposite each other. And the line I just added, which I hope you can see, shows the best fit model for these events. Now notice that the entire time that takes place over the course of the signal that we received is only about 0.2 of a second. And what's plotted on the left, on the y-axis, is what we call strain, and this is in units of 10 to the minus 21. So what is strain? Strain is defined as the change in the length of the arm of the interferometer divided by the length of the interferometer arm. For LIGO, that length is 4 kilometers, and as you saw from the previous slide, about the most strain we've seen at the peak of one of those waves was about 10 to the minus 21. So working the calculation, we see that that means that the mirror position actually shifted by about 4 times 10 to the minus 18 meters. That's an incredibly small amount. That's 4,000ths the size of a proton, which is about 10 to the minus 15 meters, or 1 Fermi. It's like if you could measure the width of your hair with a baseline over the distance to the nearest star, Proxima Centauri, at 4 light years. That's how sensitive and how precise LIGO is. And we characterize LIGO sensitivity by what we call the strain curve, which is shown here in this plot on the right. And so you see all these noise spikes, which are instrumental things, which you have to get rid of in the analysis. But you see the maximum or the minimum sensitivity, the best sensitivity that LIGO can get is about 10 to the minus 23. And that's for frequencies around 100 to 300 hertz. LIGO was originally built, tweaked up, tuned up to be sensitive to the frequencies expected from merging neutron stars. Those frequencies are higher than the frequencies that you see when you have big, heavy black holes merging. That point will be important later. So when you do the analysis and you fit these waveforms to the actual signal that we received, for this very first event, which all of them are named by GW for gravitational wave, the year in 2 digits, the month in 2 digits, and the days in 2 digits. So this was the September 14th, 2015 event. What we discovered was that the two masses were tremendously huge compared to any black holes that we had seen using X-ray astronomy that were of the stellar variety. So the first mass was about 36 times the mass of our sun. The second mass was 29 times the mass of our sun. If you see what the total mass is afterwards, it's 62 times the mass of our sun. And so adding that up, you realize that 3 of those solar masses worth of energy, using E equals mc squared, went out as gravitational waves. That is a tremendous amount of energy. That is more energy emitted in that gravitational wave than all the starlight added up that we see in the universe. This event was located at a distance of about 410 million parsecs, or about 1.2 billion light years. And the black hole was spinning, that was formed, was spinning about 2/3 of the maximum that black holes can spin after the event was over. Now, what we do to make it easier for people to relate to the waveforms is a process called sonification. Because LIGO is sensitive to a range of frequencies that is pretty close to the frequencies that we hear with our ears, we turn the waveform signals into sound waves, and then we listen to them. And as the objects get closer and closer together, the frequency speeds up, and so the frequency that you hear increases, and we call that rising intonation a chirp, like this. Whoop. And so I'm going to play you the chirps at their normal frequency, which is very low, so it won't sound too chirp-like. Then the next time through, it's going to raise it by 400 hertz just so you can see it a little better. Okay, so that's what we call a chirp, and that led to this very funny cartoon from the New Yorker that came out at the time of the discovery from these birds, which I just think is very funny. Okay, well, we made a beautiful poster out of the two overlaid waveforms and artist's drawing of the in-spiral phase, the merger phase right when the waves get really big, and the ring down phase, which is when it sort of quivers and relaxes and settles into its final state. And this is the central image from the poster. A group that I work with called Contemporary Physics Education Project sells the posters as a fundraiser. They're the same people that made all the particle physics posters. And you can find them on Amazon if you're interested in getting such a poster. And at the end of the first observing run from LIGO, which basically took place from 2015 through 2016, so then we announced this in 2017, we had seen basically 6 merging black holes. So this cartoon shows you the masses of the individual black holes, the mass of the final black holes. This event wasn't confirmed at the time, but a subsequent reanalysis confirmed that it was true, so it was changed to say GW. This is the first event that we saw, clearly much louder and stronger with bigger black holes than any of the other events that were subsequently seen in that first observing run. So just like a particle physics experiment, LIGO takes a bunch of data, then is turned off for about a year. Then you fix everything and you try to get the noise down and you try to get all of your optics cleaned up and seismically isolated and everything. So when we turned back on for the second observing run, we discovered our first pair of merging neutron stars. Now remember from when I was talking about the Taylor-Hulse pulsar, we knew that neutron stars were going to merge because we had seen examples. We did not know that black holes were going to merge. In fact, we didn't even know that there were binary black holes, much less ones so large. So that was quite surprising to everybody. This was not a surprise, but what was amazing is that we actually had data from Fermi as well. And because Fermi sees gamma ray bursts and reports them automatically to the network, the information about the burst came out before the information about the gravitational waves. But it was a very boring burst, so nobody thought very much about it until the announcement of this incredible signal of gravitational waves. So that little bell signifies that a full 2 seconds after the peak of the gravitational wave chirp, we saw the gamma ray burst. And theorists are still trying to figure out what accounts for the 2 seconds worth of delay in the gamma rays breaking out of the material that is swirling around these neutron stars that have been merged together. But it was really exciting that Fermi got into the action, and so did about a third of all the astronomers in the entire world. The paper that summarizes this observation of the first binary neutron star merger has 3,500 authors on it, and I'm 2 of them, because there were so many authors that they couldn't tell that I was on for the Fermi team and I was on for the LIGO team. Also, a lot of the authors had ground-based telescopes, and the first ground-based observers to see the remnants or the glowing embers that were left over after the merger came from the Swope telescope, people from UC Santa Cruz. And as you can see, on the day of the merger, it was bright, and by 4 days later, it had faded away. And people continued to follow this event with ground-based radio, with Hubble, with Chandra, with pretty much every telescope and satellite that's out there. It was just an amazing event that we learned so much from. And NASA got into the act because of Fermi and made this interesting animation. So this is an animation, not an actual computer simulation. And so that basically showed the merging neutron stars, the formation of the jets that make the gamma ray burst, the jets going out and plowing into surrounding material and lighting it up. And this was such a well-observed event that it's been nicknamed the golden binary. And this classic image done by my artist at Cinema State, Aurora Simonet, shows it sort of gold colored and the jets coming out and the neutron stars merging. But the reason we call it the golden binary is because the optical data that people got could be analyzed to see what kinds of elements were formed. And we now have proof that about half the heavy elements in the universe, heavier than iron, all the way up through gold and platinum and silver, are actually formed by reactions that happen in that debris cloud around the merging neutron stars, because you've got all these neutrons being sent out into these other elements like iron that were in the core of the neutron star and ending up with this R capture process that makes all the heavy elements. But for the past probably 30 years, I've been telling people that when two neutron stars merge and we see a gamma ray burst, we're seeing the birth of a black hole. And here's the first time we saw two neutron stars merge, and we're not at all sure if a black hole was merged. So I have to change my story to explain where the short gamma ray bursts come from. Because the problem is that the masses of these two neutron stars were each only about 1.2 solar masses. And when you add two things together that are only 1.2 solar masses, you get an object that's 2.4 solar masses minus some of the energy that left in the gravitational wave. So it's not clear what was formed after the merger. And we'll need to see many more such neutron star mergers and measure the black holes or measure the neutron stars and the final mass object to see what is really coming out. But it's very clear that neutron stars have a very different signature than merging black holes. So this is showing you with time, the top 5 objects are the original 5 merging black holes. As you can see, the neutron star signal that we're observing goes on for much, much longer. The merging black holes, because they're heavy and they're slow, don't stay in the LIGO sensitivity bandpass for very long. LIGO was built to see merging neutron stars, and that bandpass was tweaked up especially to be sensitive to that. And so we can see many, many cycles of the in-spiral in the waveform for the merging binary neutron star before we get to the final chirp. And so we've seen over 55 seconds of waveforms that we can fit for the binary neutron star. Now, at the end of observing run number 2, we put out a catalog of events The 4 with stars were events that we had never shown anybody before. They just came out in the catalog paper. We had separate papers on the other events. And then, of course, here's the binary neutron star, which is just so much longer. You see all of these other events are just a few tenths of a second long, although they're very bright because the black holes are very strong. The neutron star event, really quite different. So that was our first catalog that we put out in the first catalog paper at the end of Observing Run 2, which was at the end of 2017. So then LIGO turned off for all of 2018, as did Virgo, and we put in more fixes and more things to improve the sensitivity. It was turned off for about a year. Oh, here's another summary of the catalog at the end of the analysis at 2018, before we turn LIGO back on again. You see all those merging black holes measured by LIGO. You see the masses of black holes measured by X-ray astronomy, electromagnetic black holes, for the most part much lower. Here's a bunch of electromagnetic neutron stars that were measured, all about 1.4. Here's the 2 merging neutron stars from LIGO making this mystery object in what has been known as the mass gap. So between 2 solar masses and 5 solar masses, we don't really see anything because we don't see any lighter black holes and we don't see any heavier neutron stars. And it's still a mystery as to what's going on in that mass gap. And that's one of the things we'd really like to understand with more observations. So now we're in the 3rd observing run, just finished. It was cut a little bit short due to the COVID-19. We had planned to run through April, so we lost about a month. The 3rd observing run is divided into 2 parts. They took a 1-month commissioning break for the month of October 2019 to fix a few more things. And so we call it O3A and O3B, observing run A3, A, and B parts. No more electromagnetic counterparts have been found. We now have apps that you can download on your phone to alert you to triggers that we've been publishing. There have been 33 events reported in the first part of the observing run and 23 additional events in the second part. And so this figure here shows you the accumulation of the events as a function of time, so that we now know of over 60 events, 67 events total that are being analyzed. And as you might imagine, it takes a long time to analyze all those events because at the end of O2, we really still just had a handful. And now with the improved sensitivity, we're seeing, instead of 1 event every few months, we're seeing events almost weekly. That really keeps the supercomputers that are doing all the waveform analysis very busy. But it also keeps the paper writing teams very busy, and we've only released a couple of the events so far from the 3rd observing run. The first result that we released was at the January AAS meeting this year, before everything closed down for COVID. And it is called GW190425, so it happened on April 25th in 2019. It is the 2nd binary neutron star merger that we've seen. But unlike the first one, nobody else saw anything. We didn't see a gamma ray burst, no electromagnetic observations from the ground saw anything. It does make a final product that ends up being 3.4 solar masses, so right over the 3 solar mass lower limit that we've calculated is where black holes can form. But what that means is, if one of the neutron stars is 1.4 and we end up with a total mass that's 3.4, then either one or both of the original neutron stars were heavier than 1.4 solar masses to start with, or it could have been a merger of a small black hole with a normal sized neutron star, and then some energy leaves and you have left a little bit bigger black hole. It's hard to tell. We need more examples in order to get any further understanding this one. And the second result that we put out is actually happened a couple weeks earlier, but just takes time to figure this stuff out. It's called GW 190412. It was detected by both LIGO and Virgo. This one is unique because it's the merger of two black holes that are really, really unequal in mass. And so when you have such a mass disparity, and because gravitational wave radiation is quadrupole in nature and not dipole like electromagnetic radiation, you expect to see higher harmonics in the waveforms that you fit to the signal that you see. And in fact, these higher harmonics were seen as predicted by general relativity. Also, when the masses are so different, it allows you to fit the waveforms better and get more precise distances to the system. This one is about 2.6 billion light years. You can do a better job of measuring the spin of the heavier black hole. So before the merger, you can actually measure the spin of the black hole. And you can see precession in the system. You can fit for precession of the orbit. And then the next slide, I'm going to show you. Now, this is the last 30 milliseconds, so it's greatly slowed down. This is another one of these simulating extreme space-time computer simulations done by that group. So this is a full general relativistic supercomputer calculation that took, weeks of supercomputer time. So we see here the big 30 solar mass black hole, the smaller 8 solar mass black hole. When the colors are blue and green, the waves are weak. When the colors turn into reds and oranges, the waves are stronger. And so we'll start up the animation here, or simulation. See them orbiting each other. You can see the time on the bottom. So that was only, 5 milliseconds worth of time so far that went by. See the interesting wave patterns that are coming out as the two are orbiting each other. Now it's going to have a little inset blow up of the action where the two black holes are near the center. See some of the red colors is starting to happen now as the black holes get closer to each other. It's getting brighter. Brighter and brighter. Now it's going to freeze the movie so when it gets close to where the black holes merge, so you can see the merger process. The waves are really bright. In the last millisecond, freezes the movie. You can see the precession of the orbit of the smaller object around the larger object. Then they merge. Then it sort of relaxes in shape and ends up spherical again. And you get the big blast of waves from the final merger, and then it's over. So that's a pretty awesome calculation, I think. And okay, so that's all the data that I can show you. Sometime next week, there may be a new press release that is coming out from LIGO. We're expecting it to come out next week. I can't share it with you, unfortunately, because it's not coming out till next week. So stay tuned for that. But if we look around the world, we have quite a few observatories now. Here's the two original LIGO observatories with 4 kilometers. All of the recent results I've shown you were done with Virgo, which is near Pisa, Italy. That's 3-kilometer baseline. The Japanese Kagra detector is underground and cryogenic and just came online and has joined the very last part of observing run 3. But then unfortunately we had to close down early, so they haven't been able to detect anything yet. GEO 600 is just a short experimental 600-meter long baseline that we use for testing instrumentation, and that looks for supernovae when everything else is shut down because it's the only one that continuously runs. And then just started the construction of LIGO India. Now, why would we want to put one in India? Well, actually, what we wanted to do is put another one in Australia. So we would have coverage of the, better coverage of the sky and better positional information about the different bursts. But unfortunately, the Australians couldn't afford to do that. And so the best we could do in terms of getting something towards the south was in India. And they are getting an exact copy of the LIGO detectors and mirrors and things. And then they are building their own beamlines and tubes and lasers and all the infrastructure. So we were hoping for LIGO India to come online in about 2024. So that will be exciting to have even more coverage. But I also want to mention that gravitational waves, just like electromagnetic waves, come in a range of frequencies. LIGO and Virgo are at the high end, okay? So they're sort of the equivalent of gamma rays in the electromagnetic spectrum, right? They are the fastest frequency waves. And if we want to see slower waves, what we need, well, not, if we want to see longer waves, they all travel at the speed of light, so I misspoke. What we need is a longer baseline. And so the next longer baseline project is called LISA, Laser Interferometer Space Array, or antenna. That would be shooting laser beams between 3 different satellites in space that are all maintaining their distances, or at least tracking their distances, 5 million kilometer baseline instead of 4 kilometers. Okay, that is in the planning stages. There have been some test runs of some space hardware, but it's not being built quite yet. What is happening are these really, really long duration waves, where one wave would be of order years to decades just for one wave, the frequency period, whatever. So that's being done by an array of ground-based radio telescopes called nanograv, because these waves are in the nanohertz frequency range. That's how long they are, how slow they are. And so you've got millisecond pulsars all over the sky, between 30 and 50 of them, a lot of which were discovered using Fermi with the radio astronomers together. And if a really long wave goes by, then what happens is the timing of the pulsar signals gets perturbed in a very predictable way as the space-time stretches and compresses as the waves go by. And so they're studying these millisecond pulsars, which are incredibly accurate clocks, and they're trying to figure out if any waves are going by, but they haven't seen any yet. They still keep working on it and improving their sensitivity. And then the longest possible waves would be imprinted on the cosmic microwave background polarization signal. And these waves were erroneously reported by a group of people with an experiment called BICEPS. So if you saw any news about that a few years ago before LIGO announced the real waves that were discovered, you can go read about what was expected. But the gravitational waves that were formed at the beginning of the universe in the Big Bang should have left a specific polarization signature imprinted on the cosmic microwave background. And people were looking for that signature, but as the Planck satellite later showed, what the BICEP people reported was really just due to dust. So that was sad. It doesn't mean it's not there, it just means it's not as strong as they were hoping, and they have to keep looking. So we have a whole range of gravitational wave frequencies where we can study bigger systems. So for example, LISA can look at merging supermassive black holes in the cores of galaxies, and so can nanograv. So that will be work to be done in the future, the next 10 to 20 years, I would guess. So we now find ourselves at the beginning of the era of what we're calling multi-messenger astronomy. We are putting together signals from electromagnetic waves, from gravitational waves, from cosmic rays, from neutrinos. So these are all the different kinds of detectors, satellites, air shower arrays, neutrinos, gravitational waves. Each type of messenger tells us something new about our universe. When we put together all of these different kinds of information, we get a much more complete picture of what's out there in the universe today. Similar to when I first started my career in astronomy, people were just starting to put the wavelengths together. So they were looking at X-rays, and then we'd also look at visible light, right? So we had multi-wavelength astronomy 40 years ago when I started, and now we're into multi-messenger astronomy. Quite in advance. Okay, and I will leave you with a slide full of links that you might want to look at to learn more about these things. The main LIGO website, the page where all the detections are. We have some course materials that are free that people, if they want to learn more about GR or about LIGO and how LIGO works, feel free to go there. You can hear a lot of the sonification things at this website, soundsofspacetime.org.
Yeah, thank you, Lynn, for the fascinating talk. Does anybody have questions?
Maybe you can tell us a little bit about how you obtain positions in the sky. Like, how do we know, for instance, that the first Fermi detection was coming from the same place as the gravitational wave detection?
Okay, so this is what happens. For each LIGO detector, you got a great circle on the sky.
Mm-hmm.
Okay, because you're looking at the time delay between the time the signal comes in at LIGO Hanford and the time the signal comes in at LIGO Livingston. And so that gives you one great circle on the sky. Then if you get another detector, then you get another circle. So you get a circle from Virgo. Okay, so then when the circles overlap in a couple places, that narrows it down to just a couple places. Well, it's not quite so simple for the one with Fermi. The binary neutron star one. So it was very strong. It was detected by both LIGO detectors. It should have been able to be seen by Virgo, and it wasn't seen by Virgo. Okay, so what that means, this is where it gets a little subtle, is that the Virgo antenna has some dead patches in the antenna pattern. Okay, so it has the beam pattern, and then it has the places in between where the beams are strong where you don't have very much sensitivity.
Right.
What that meant was that for Virgo, it was in one of those dead patches. So that narrowed the location down even further. And in the case of Fermi, Fermi is behind the Earth, and then it's not behind the Earth. So the Earth blocked out a big part of the sky because Fermi could see it, so it wasn't behind the Earth. When they put all that information together, so when you put all that information together, they ended up with a very, very small position on the sky that then really helped all those visible light astronomers find the galaxy. So that was a particularly complicated story, but normally what we would expect is a bunch of overlapping great circles on the sky, and when Kagra in there, we'll get another great circle, and that will really help narrow down the positions.
Kind of like what we did with Uhuru in the early days of X-ray astronomy.
This it reminded me a lot of the earlier Uhuru days, for sure. So without all of those interesting things that happen with that particular event, you end up with positions that are about 600 square degrees that you have to search for changes. With a visible light telescope, or even with Swift, it's almost impossible.
Yeah.
I was very lucky the way that first one turned out. Any more questions?
Go ahead, Connie.
I'm curious if you don't mind going into a little more detail about some of the optics in the actual initial LIGO detector. So some of the ways in which the lasers cleaned up and then split, and how the it looked like there were mirrors and different.
Oh, there's all of those little things were different mirrors, and so the output mode cleaner, what they do is there's a frequency spread even in a really good laser beam, and so they narrow the frequency back down to try to keep it as monochromatic as possible. With the power recycling mirrors, they just bounce it back and forth a lot and make an optical cavity that's in resonance that will store that extra power before sending it down the beam. And then, of course, there's this big 40-kilogram chunk of glass at the end that's the mirror that reflects the beam back. And the key there is to have a special coating on the mirror so that as the laser beam spreads out, it's about 6 centimeters wide at the end when it gets to the mirror. So the key is not to heat the mirror up very much, because that, of course, will introduce all sorts of thermal noise while you're trying to reflect the thing and get it to go back down the beam line. So there's an incredible amount of very, very complicated optics, most of which is beyond my limited experimental ability to recreate myself. But if you're interested in learning more about the noise sources and the different parts of LIGO, the 2016 LIGO course that's online at that link I provided has really nice calculations that help you understand a lot of the noise spikes in the sensitivity curve, where they come from, and what the different kinds of noise are that LIGO is constantly battling. One of the things we're going to be putting into the next version of LIGO is a thing called squeezed light, which is really impossible to explain. I would Google that and listen to a talk by Nurgis Malvavala from MIT if you want a better understanding than I can convey. But what you're basically using is the uncertainty principle to narrow down the light in frequency space while letting it expand in phase space, which you don't care about. And that helps you boost the signal from the laser. Because you might imagine increasing the laser power would help you, right? But then it heats the mirrors up too much, right? So you're constantly trying to balance this thing between the optics and the mirrors and the frequency, and trying to optimize the things that you need for the detection.
Fascinating. Cool. Thank you. I'll definitely check out that LIGO course.
And for the person who wrote in a comment that they didn't get to see too much, this is recorded, and the recording will be made available to everybody so you can watch it at a later time. So hopefully that will work for everyone.
Lynn, this was great.
Well, thanks, Terry.
It was.
It was nice seeing you. It's been an incredibly exciting project to work on.
Yeah.
There's 1,200 people in the LIGO and Virgo scientific collaboration. We just added COGRA, so now we're calling us the LIGO Virgo COGRA collaboration. And it's just a really wonderful group of people to work with. It's been tremendously exciting for me to be able to study my old friends, the binary neutron stars and the black holes that I started off with you way back when in X-ray astronomy, in this totally other messenger way. So it's just been a lot of fun and very exciting for everyone. And I hope that all the National Science Olympiad folks enjoy this talk and get to learn more about LIGO.